Ah, good. Oh yeah, yeah, yeah. No. Okay, sure. Wait, do you have the soft copy?
No.
Oh. Then why are you taking our phone?
Photo of it.
Oh, you have the photo. Why do you have the photo of it? Okay, I don't want to know. I don't want to know. I don't play that kind of game one, dude. Right? If you have it, then good for you. Let me teach you already. Then maybe you know how to fill in the numbers. Then okay, fine, right? That's it's on you, right? But I'm not gonna give you the answers from the test now. Yeah. Not that I what integrity or anything like that. I already go and steal the revision village stuff, right? But I'm just thinking like, no lah. I think I will also want you to learn how to do it on your own, huh? Okay. Let's play the long game, right? All the way to IB exams, okay. I can spoon feed you the answers now, right? But by by experience, like your year six, right? Your seniors, over last week I got 5 inquiries. Yeah, you know why? Because after the CTs, all of them all fail. Like 20-30%. All of them all fail. All of them all coming, huh? Yeah, Shane, yeah. No, all of them all like they realize that the having pictures like this, right, and scoring very high, right, last time, right, doesn't work anymore already. Stupid lah. Where do you think it will happen? What do you think will happen? Of course, this, right? Hey, do you have this set of notes,
No.
Yes, no, maybe. All print out, I print out, for everyone. Okay, I print out, Which one? You got that wrong. Yeah, you didn't even attempt for polarization, what? You did, man? Okay. But that one was a trick question. Don't get tricked, right? Because when I saw that they said unpolarized light, I know already. Right, they're trying to trick the students. Ah,
Never mind.
it's okay. It's okay. Right, it's fine. Right, play the long game. Right, they're looking at IB. Right. Try to count the number of lights that we need. We need LED tubes now, you want? Change everything. That time Ian he can put in put in and work already. Yeah, let me take away starter. How you take away starter? You take away starter and then connect the wires. Oh. That means the starter is in parallel. 9.4. How does anyone understand anything in school if they go through so fast? How does anyone understand anything in school if they go through everything so fast? Like 5, 8, and 3, right? In the last, what, 2 weeks? Yeah. I don't understand how, Which part of? Oh, 5, 5. 5, he says that. I guess. I mean, there are some parts, but they are very small parts, Like there are new things like internal resistance, which you should spend some time teaching, right? There are new things like Kirchhoff's law, which you spend some time teaching, right?
He said, like the end of his previous lesson, right? Yeah, 40 minutes. And then he was like, oh, I just one whole lesson to do questions. So I'll just give you guys a quick. And then he went out.
I need one whole lesson for Kirchhoff. With 40 minutes left. I can teach Kirchhoff's law in 40 minutes though.
Then he went for whatever it is.
I just met up with the with your great grand seniors that has the same rotation of teachers as the ones that you have now. Yeah. And then basically That batch was also a very big batch. That batch was like 30 something. By year 6, it hit 30 something already. The whole group. Yeah, not one class. I mean, split into many classes, right? But that batch was like 30 something students. Wow, it was bad, man. The Lokam Leong Benchan, and so I don't get a lot of Benchans. I mean, understandably so. But I get a lot of Fukamings and Lokam Leongs, yeah. And yeah, I don't understand that. It's okay, it's okay. Just okay. You know why you're here? You're here because you want to make your life efficient. You can, honestly speaking, you can study all this on your own, right? Guarantee. You can study this on your own, okay? But you might, the idea is to cut out the frustration, the inefficiencies, the all the unnecessary like hardships that you have to go through unnecessarily, right? So it's ridiculous, okay? You go out into the business world, right? Everyone says, oh, you should have a mentor, you should have a mentor, you should have a mentor, right? Then when it comes to studies, oh no, you should do it on yourself. What bullshit lah. Go home and dwell on this thing. This thing is useless one. Physics is useless. I, you heard me say this before, right? Physics is one of the most useless subjects. I love chem and bio. I cannot teach chem and bio only. I love them as a subject because it's so easy to me. Chem and bio is very easy to me. I can just look at the textbook and understand everything. Because you just need to memorize for me. Physics is useless. Really? Do you need to know this? Who cares about this shit? Waste time on it, right? Okay, so my job is to just help you understand this nonsense and make it as easy as possible for you so that you don't go home feeling very stressed and you can spend your time doing other things because you need that time. I guarantee you by next year you'll be very overwhelmed. It's the IB life. Next year, April, right, you'll realize what the hell are you doing in IB? Okay? Right? But my job is to make sure that you guys get drilled into this one, you remember this so that you don't have to fret about it next year. Right? So I'll just tell you for physics, don't worry. Okay, next year. Now you don't have to worry also, right? Now you don't feel the pain yet. Next year you feel because your EE, your EOK, your IAs, all your IAs and everything. Even for your IA with me, right? I will try to guide you along, try to help you. There's gonna be some work, but at least you're not going around aimlessly. I will tell you what you need to do in order to proceed. Okay, right? I'll guide you along, but you don't. Like, I think the pain of not knowing what to do next. That's the most overwhelming part. Right? So at least I'm here around here to just tell you, you just follow these instructions, right? You just go this way, like this. Okay, can right? Just to reduce your pain, right? I'm basically your punching bag, right? Just to you can unload all your woes on me, but okay, fine, right? Then we just go on. Let's do resolution now. Okay, there are two words I need. There are two phrases I want you all to remember. There's one word called resolution, and the other one called radius criteria. They're different, they're not the same thing, okay? Right? They're slightly different. So resolution. So there'll be questions like this. Ask you, okay, define resolution, or explain what resolution is. Okay? So resolution is basically the ability to distinguish one image from another. That's all. If you can distinguish two objects or two images from one another, it's considered as resolved. If you cannot, then it's unresolved. But it sounds very subjective, right? It sounds, because some people might be able to, some people might not be able to, right? So, but that's what resolution is. Resolution is just like just the idea of being able to distinguish two images from one another. Okay, Rayleigh's criterion is the mathematical requirement criteria to be considered resolved. Whether or not you can see it, it doesn't matter. Rayleigh's criterion tells us that you should be able to, right, based on its mathematical proof. Right, we'll go through that in a while. Right. The next thing is I want to backtrack on this resolution thing, right? So resolution is not about sharpness. When an image is resolved, it doesn't mean that it's sharp. It means that you can distinguish it from another image. That's what it means. So don't go and talk about sharpness, don't go and talk about contrast, don't go and talk about the ability to focus on the image. It's not that at all. It's just about your ability to distinguish it from something else. Okay, so there are three pictures here. We'll go through these three pictures in a while. Let's start off first by understanding resolution requires what? You require an optical instrument. Give me an example of optical instrument.
Magnifying glass.
Magnifying glass, okay. Anything else? Telescope, anything else? Eyeball, good. Anything else? Camera.
Just a lens.
Yeah. I mean, yeah, the lens, right? So for resolution, we will usually use it for eyeball, camera, telescope. We won't use it so much for magnifying glass or microscopes. Okay, right? Because the idea is that these objects are very close already. You can find them already. Right? So telescope, far away objects. Basically, we're always concerned about far away objects. So telescopes, right? Eyeball camera. Right? And in order to understand resolution, we first have to understand that the eyeball, the camera, and the telescope all have a hole for the light to come in. What is the hole for your eyeball called?
Iris.
That's not a hole lah.
Oh shit.
Yeah, the pupil lah. The iris is the muscle near around the pupil, right? The pupil is the hole, right? It's basically just an absence, right, of anything there. That's the pupil, right? Okay. So if I were to draw for you something like that, you should understand that this is the pupil of the eye. Then this is the screen at the back of the eye. What's the screen called? Cornea is at the front now. Cornea is the you don't take bio, man.
I don't remember.
Hello, you took bio. You got cut the eyeball, right? You got cut eyeball, right? Do you cut the eyeball in that? No, wow, last time they let us cut eyeball, then fun, man. You just take
Human one.
not human lah, dude. They go buy cheap eyeball lah, bro, from the market. Who? Man, half the text, yeah. Okay, no. Okay, if I say the thing you know is retina. The screen is called the retina. Okay, yeah, right? Okay, good. So the idea is you have an object far away, and the light from this object is going through, right, this pupil. Okay, so the light is going through the pupil. So the light goes through the pupil and then it lands on your retina. Okay? Can? Now, resolution doesn't apply here. Because there's only one object. There's only one image. It doesn't make any sense. When you want to talk about resolution, you need to have two objects, to have two images, and your ability to distinguish these two images, right? You only got one only. There's nothing to talk about for resolution here. Okay? Right? Okay, so we need to introduce another object, but later. So for now, we understand that this object, right, the light is passing through the pupil, hitting the retina, so passing through the instruments, right, hole, right, the aperture, okay? Right here, right now, I need you to flip out the addendum. Don't know whether you remember having this addendum or not. Do you have this addendum? The one where, the one last week I gave you this one. You have this sheet of paper? You have, huh? Okay, bring it out, bring it out. Okay, I want you to look at this one here. So if you have light going through a circular aperture, and you should know that your pupil is a circular aperture, it's not a slit. You're not a cat. Right, cat, the pupil is a slit, right? But you're a human being, so your pupil is a circular aperture. If it's a circular aperture, right, then this is the pattern it makes on the screen. Right, you see this pattern here? So this pattern will have a central, like, you know, it becomes rings like this. So it looks a bit different. It looks a bit different from single slit, right? I mean, guys, let's do a bit of recap, right? How does a single slit pattern look like then? If you take a light and you shine it into a single slit, right? How does the pattern look like on the screen? Anyone?
Central max, then
Uh-huh.
you short one from either side.
Where? What? What is it? What is it? Dots, is it? Okay, yeah. So basically you have one central max in the middle, then followed by like weak ones, right, on the side like this, right? Okay. So for a slit, the pattern looks like this. For an aperture, the pattern looks like this. It's basically you take this one, right, this pattern here, right, and you rotate it 360. Imagine you rotate it 360, it'll look like this. You know what I mean? But recall again, single slit, what's the most two important features? Central max, first minimum. Central max, first minimum, correct? Central max and first minimum, right? For single aperture, also same. Central max and first minimum. You see where they label the black lines at? Central max and first minimum. Right or not? In fact, I don't like this diagram because of the subsequent rings that they draw. Right? Technically, the subsequent rings that they draw is what? Very weak one, right? Very faint one, right? You're not supposed to be able to see it. Right? So the most important 2 points here on this diagram is also the central max and the first minimum, where the two black lines are, like this. Right? But when you have a central, when you have a circular aperture, right? When you have a circular aperture, the equation is theta equals to 1.22 lambda over b. All right. If it's single slit, what's the equation? Theta equals to lambda over b. There's no 1.22. The 1.22 is just a correction factor. It's a correction factor that corrects it from single slit to aperture. That's all, right? So when you see the word aperture, aperture means hole, circular hole. Okay, huh? Right, aperture means circular hole. Okay, right. But between these guys, this one here and this one here, this one here and this one here, right? If let's say I do a cross section, I do a cross section across and do a cross section across and I draw the graph. How does the graph look like? I want to draw the graph. How does the graph look like? Okay. How? Yeah. How does the graph look like? You draw across. You draw it on the graph. Draw a graph. How does the graph look like? How does the pattern look like on a graph? Okay, be very careful. Which one? No. That's double slit. Right? If it's like this double slit, right? Because even, right, is like that. Correct or not? Hey, I say you have to remember all four, right? Yeah, you have to remember all four. Right? You have to remember all four patterns. Okay, so be it circular aperture or single slit, right? Actually, the graph all looks the same. The graph looks like this. Okay, the graph looks like this. Wait, I draw for you. I ask you, does it look like that? Is this single slit? Why not? This looks more like what? Modulated double slit. So this one cannot be single slit. So that's why I said just now, right? Because you went to draw a little bit higher just now, right? So I was like a bit worried. You might be thinking that it's a bit high. It's not. It's like insignificant one, right? So the side ones are like that. This is single slit. Single slit or single aperture, same. Okay. So back to my original question again. So let's say you draw your pupil here. All right, how big is your pupil, by the way? How? Estimate. 1 cm? You're on drugs, You think, hey, your pupil is the whole, not the entire black area. The entire black area is the iris, bro. You really hate bio, Right, not 1 cm lah, right? Less than that, about 2 to 3 mm. Okay, 2 to 3 mm. You know, right, when you go into a bright place, what happens to pupil?
Straight.
Right, constricts, right? Okay, then it's smaller, right? Then you go into a dark room, it widens, right? Then you high on drugs, even wider, right? Okay. Not that I know lah, right? Okay, right. That's what the medical journals tell me. Okay, right. So an object that's very very far away, right? The light is passing through the pupil. Pupil are not lens, not cornea, pupil hole. Okay, right? The pupil, not lens, just the pupil. Okay, when it hits the screen, right? What sort of pattern does it make? The single aperture pattern, right? This just basically looks like this. Okay, so I'm gonna draw it. I'm just gonna draw it like that. Okay, you know what? Let's say the slit is narrow. Let's say the slit is narrow. Okay, let's say the slit is very very narrow, very very narrow slit. Okay, this theta equals to 1.22 lambda over b, right? If the slit is very very narrow, what will happen to the theta? Big, right? The theta will become very big, right? What that means is that your pattern will become very wide, right? So I'm just showing you this is a very narrow slit, and I'm going to show you that what happens to the pattern. The pattern becomes like that, very very wide. Okay, then let's talk about resolution. In order to talk about resolution, I need to bring in another object. So I'm bringing another object now, like this, right? I bring in an object that's nearby, like this. Okay, and the light is going in like that, right? The light is going in also like this. Can? Right, light is going in, Wait, hang on, let me just bring it slightly further away, something like that. Okay, don't worry if you realize that you're not able to draw exactly like mine, right? I think the whole idea is that I just want you to draw for the sake of learning, right? Doesn't really matter whether you get it the right drawing or not. But I want to ask you this, okay? So this light is coming from another object, right? This light is coming from another object. It's the same wavelength. Both their wavelengths are the same. So this one, the lambda here and the lambda here are the same wavelength. That means maybe it's a certain color or whatever it is, right? Same wavelength, and they pass through the same aperture, right? Pass through the same aperture, which is same B, right? I'm gonna ask you this, okay? What will the spread of the other object's light be like on the retina? Is it going to be identical to the same? Is it identical to this spread?
Yes.
Yes, right? It's identical. You understand, right? Identical, So you will never ever get a situation where you got one wide spread and one narrow one. It makes no sense. Both these lights are coming from the same wavelengths, right? Coming from two objects, same wavelengths, right? And going through the same hole, you will never get a different pattern. They will be identical to each other. So the other pattern will look like this. Right? I try to draw it as symmetrical as I can. What's the problem with this? So yeah, what's the problem now? They overlap, right? They overlap too close, right? They overlap too close. If you overlap too close, what happens? If you overlap too close, what happens? Right? If you overlap too close, if you look at the next page, right? I do have a picture here like this. You see, when they are too close, right? When the overlap is too close, they form a combined image here, which doesn't even show you like two objects. So even though there are two objects out there, by the time it comes into your eye, you think there's only one. You think there's only one image. This will be considered as unresolved. But you wouldn't know actually, right? You as an observer wouldn't know until you make some changes to it. Okay? Can? Alright, so you wouldn't know that there is two objects until you make some changes to it. But for now, if it's unresolved, it looks like this. right? Just one bright spot of light like that. You are not able to distinguish two images from one another. This is called unresolved. Poor resolution. Okay, let's think about this first. So how can you improve resolution? Take note, I always want better resolution. It's like a given. You always want better resolution. It does not make sense for anyone to request for poorer resolution, right? I want a lower resolution monitor. Nobody says that, right? Right? Everyone's always going for the higher specs, right? Okay, how can you improve the resolution here? Like just with this picture, nothing else. Okay, if you notice, if I want to improve resolution, right, there's actually two factors here. There's lambda and there's b, right? Lambda will be the wavelength of the source of light. But if you can't change the source of light, then this is the lambda you have to rely on, right? So the only thing that you can change is b. How should you change b in order to improve resolution? Okay, so general rule, make b as big as possible. You want a bigger aperture, as big as possible. All right, so I'm going to give you an extreme. So I'm going to show you an extreme. I'm going to widen this b until it looks like that. Make it super wide, no longer narrow. Okay, obviously your pupil can't go super wide, right? Correct or not? There's a limit to your eyes, right? What I'm saying is that use a camera instead lah. Use a telescope instead. Use a big ass telescope instead. Right? Okay. You make the hole right where the light can be received as big as possible. Can? That means you widen the aperture. Can? Now, if you have a very big B, what happens to theta?
Bigger.
Eh?
Wait.
Your math lah, bro.
Smaller.
The theta becomes very small, right? That means what? What happens to the spread?
Thinner.
Right? It becomes narrow, right? So this is how it looks like. It becomes like that. When you increase the aperture size, the diffraction patterns of the individual light becomes very narrow. Right? They become very narrow like this. And then that means what? Less what? Less overlap. Less overlap, right? We won't use the word interference here, okay? Right? So less overlap. So if it overlaps less, that means more distinct lah. You understand this? Okay. So I want you to look at this equation. And I want you to remember something about this equation. This equation gives you the spread of the pattern. Right? It gives you the spread of the pattern, right? And it's based on what? It's based on the instrument that you use. Right? The bigger the B for the instrument, the smaller the spread, right? The better, right? So just remember this, okay? You want this equation, you want this theta to be as small as possible. Right? You want this theta to be as small as possible. The smaller the better. So you can use a very, very big B, a very, very big, right, aperture, right? And then you can make theta as small as possible. What's another way of making this theta as small as possible also? I mean, if you don't want to change the B, lambda, how do you like what lambda are we talking about? Huh? Okay, so different light sources, right? But if these objects are very far away, like stars, right? You can't go over to the star and then change the light source and then come back, right? Right or not? Right? So you can't change it. But here's the thing: stars do what? Stars produce all sorts of wavelengths. Stars produce everything from radio waves to gamma rays, the whole range. Right? Even our star also, the sun. The sun produces everything from radio waves to X-rays. Okay? So what you can do is you can change the sensor. You can change the sensor to detect different lambdas. Our eyes can only detect visible light, right? Which is what? 400 to 700 nanometers, right? Okay? But you can change the sensor and maybe you let the sensor detect UV rays. Why UV rays? No, as in like, why would I choose UV? That means I was using visible light at first, right? Then I said to improve resolution, maybe you can use UV rays. That means you change the camera to use to detect UV rays. What's up with UV rays? Shorter wavelength. UV short, you have to remember this, huh? How short? Less than? Anyhow where? Less than 400. Less than 400 nanometers. 400 is what? Violet, right? UV is ultraviolet, right? Less than 400. Shorter than 400. So it is a shorter wavelength. So if your camera is adjusted to detect UV rays, right? If your camera is adjusted to detect UV rays, you can improve resolution, which means that now we observe UV rays from these objects. If it produces UV lah, right? If it doesn't, then cannot lah. Okay? And then therefore the patterns will be even more narrow now. Right? The patterns will be even more narrow like this, right? I'll show you. And the patterns are even narrower now. Why? Because if you use shorter wavelength, if you observe from shorter wavelength, your detail is going to be smaller, right? The spread is going to be even smaller. Okay, Can? Alright, so there you go. Right? So the whole idea is what are the ways that you can improve resolution? And you always want to improve resolution. Okay, now so if your B is narrow, this will cause the pattern to be very widespread. And if it's very widespread, then overlaps cannot be resolved that way. Right? Okay, so now the thing is, I need you to learn another angle. This other angle is the angular separation between the objects. Right? This one is the angular separation of objects. Angular separation of objects. Okay? I'll just tell you straight away so that you don't have to do any more guesswork. Theta here is basically equals to x over d. Right? Theta equals x over d. But this is not the x over d for the single slit. This is the x over d for the objects. Right? This is not the x over d here. You understand this? Right? The x over d is the angular separation of the objects. It's not the x over d here. There is also an x over d here as well, but that's for the single slit. You don't need that because you already have this. Right? You already have the theta of the instrument. So this is instrument theta. You want this to be as small as possible. This is objects angular separation. You want this to be as big as possible. But there are sometimes you can't change this. I mean, like stars, right? Can you move the stars apart from each other? Can you make sure they go further away from each other? Cannot, right? Then you can't also really move closer to them as well. Right? Despite us launching space telescopes out into space, right? The how far we are away from the stars is like in light years or no. That sort of small distance doesn't make a difference. Right? It doesn't make a difference to observing the stars. So the idea here is sometimes you cannot change this at all. This cannot be changed. Right? So most of the time, even though we want this as big as possible, right? Sometimes this cannot be changed. You understand this? Right? Especially for immobile objects, right? Like or distant stars. X and D cannot be changed. So that means that if you want to resolve a picture of stars, right? If you want to resolve an image of stars, the best you can do is actually just these two only. You either shorten the wavelength that you're observing or you increase the aperture size. Okay? So the bigger the telescope, the better the
resolution.
Good. The bigger the telescope, the better the resolution. Right? For all of you, remember this now because astrophysics also need this, imaging next year also need this. Right? Remember this because this actually sets a prelude for your next year's topics, the options topics. Okay? Can? Okay, good. Right. So this one here, you want it as big as possible. Big as possible. All right. And I need you to understand this. Do you see this detail here? Can you confirm with me that it's the same detail at the bottom here, like this?
Yeah.
This is the angular separation of the patterns, right? The angular separation of the patterns. And then yet when you have a pattern, right? Let's say the pattern spread looks like this. Let's say the pattern spread looks like this. This will be the angular spread of the pattern from this. So this, how far this pattern spreads, it depends on the wavelength and the aperture size. How far these two patterns are away from each other, like, you know, the separation of the patterns, right? The angular separation of patterns depends on this here. You understand that? Good. So got two details, right? Yeah, got two details. I tell you, your teachers don't teach you by details. Your teacher does not teach you by this angle or by this angle. They simply just teach you this. They take this equation, they say that it's less than or equals to this equation here. But nobody understands what the heck is going on. All right, so let's say, I'll now give you the scenario, okay? All right, the scenario is this. Let me just drag it somewhere first. Okay. If 1.22 lambda over b is, if you calculate 1.22 lambda over b, is less than, right? Is less than the x over d. If they give you the x over d values, right? Is this resolved or not resolved? Okay, let me put it in words. You see the equation here, but let me put it in words to you, okay? If the spread of the pattern is narrower than the angular separation of the objects, is it resolved or unresolved?
Resolved.
It's resolved. Don't forget, you want this as small as possible. So if this is smaller than that, then it's resolved. Okay? Right? It's resolved. Okay, it's about the pattern here. It's about the pattern here. Right? You see this, right? So this is the angular spread, right? This is the angular spread. Sorry, this is the angular separation. This is the spread. If the spread is smaller, that means I make it as small as possible. That means that you can see that the spread is like narrow and like that. If the spread is like this narrow, then can you see that the angle, this detail here is this angle here, right? It's smaller than the separation. Like this is resolved, right? Because your two patterns will look like this. Got overlap? No overlap. That means resolved. Yes. Okay. So if your pattern spread has an angle smaller than the separation angle, then this is considered as not just resolved. No, this is considered well resolved. This is well resolved. That means it's very clear that there's two objects already, there's two images already. It's considered as well resolved. But what happens if it's more? Let's say you calculate your 1.22 lambda over b, it's more than the x over d. That means the spread is bigger. The diffraction pattern has a bigger spread than the angular separation.
It's not resolved.
It's not resolved because of overlap, right? Because the pattern is too fat already. Okay, so this is not resolved. What happens when it's equal? So 1.22, if let's say you calculate and you realize that 1.22, or they tell you that, you know, it is equal, right? What does that mean? Just resolved. Good. All right, just resolved. Right, this is just resolved. Okay, so if your instrument's angle matches, all right, the angular separation of the objects, the two images will be just able to distinguish from each other. This is called just resolved. Some teachers, will be annoying and change the question to, they tell you that these two images are just not resolved. It's the same thing as just resolved. Yes, that's my point. So some teachers will write that down in the exam and then, like, confuse the students. What do you mean by just not resolved? Same thing as just resolved.
Wait, so is it resolved?
Huh?
So I don't what's just resolved?
Just resolved is that fine line between being well resolved and being not resolved. Yeah. Right? So, but it is considered as you just can make out two images. If it's any worse than that, then it's badly, there's not resolved. And if it's better than that, then it's called well resolved already. Right? So just resolve is that fine line. This is Rayleigh's criterion. Right? So if you notice the term Rayleigh's criterion only talks about images being just resolved. So this is Rayleigh's criterion. That means you have just met Rayleigh's criterion. Sorry. Right? Rayleigh's criterion is met. Right? So mathematically, it's like that. Right? 1.22 lambda over b is equal to x over d. That's meeting Rayleigh's criterion. Okay. Alright, so this is just when the instrument, the pattern spread is equal to the angular separation, when it's just resolved, right, the picture looks like this. The graph looks like this. Okay, you don't have to draw this, but I just want to show you that this is the angular separation, right? This is the 1.22 lambda over b, right? The pattern spread. This angle is now equal to this angle. Just nice. Okay? So for Rayleigh's criterion, the requirement is when the central maximum of one source coincides with the first minimum of the other. Central max, first minimum. That's why I say, right, single slit, right? What are the most two important points? Central max and first minimum. Everything depends on it. Guys, incidentally, right, if the central max of one pattern coincides with the first minimum of the other pattern, the other side also coincide. For sure one, guaranteed. That means if it coincides here, it will also coincide on this side as well. Why? Same wavelength means what? Yeah, so the spread of each pattern is identical. Like I say again, you will never get what? One fat one and one thin one. You will never get such a situation. Right? It will always be identical. So if the max of one of them matches the min of first min of the other, then the max of the other will match with the first min of the other one. Confirm, guarantee one. Okay? Okay. So that will be for just resolve. So when you are asked to define just resolve or Rayleigh's criterion, okay, you don't have to write down the equation. You just simply say this. Rayleigh's criterion for just resolve is when the first dark fringe of one coincides with the central max of the other. Okay, can okay. So the best thing to do now is just to jump into the sum of the practices here. So let's just jump into it. So you see this picture here, this one here is all something that we've already done on your own, right? You draw it on yourself, so you don't have to worry about this anymore. Right? Let's just do this one. Okay, let's do the practice for this one. All the answers here are all wrong one. So we have to go and calculate the right answers. So spy satellite 300 km above Earth's surface, lens has the diameter of 40 cm. Estimate the smallest separation that the camera can resolve on the Earth's surface, assuming that light of wavelength 500 nanometers is used. Right, let's draw out the scenario first. Okay, you got a spy camera, eye in the sky, like this, right? And then there's the surface of Earth here, like this. There are two points on Earth. You gotta have 2 points on Earth, right? So it's the smallest separation, right? So the separation is this one here. They're asking for x. Okay, they want to know what's the x here. Okay, they want to know what's the distance x between 2 points, right? That can be resolved by the lens. Okay, all right. So the camera here like this. So I guess the whole idea is that, if you want to look for the smallest separation that can be resolved, you're looking for just resolved. Okay, and if you still a bit confused by the patterns and all that, right? Then you just simply just write down the equation. What's the equation for just resolve?
1.22 lambda over v equals to x over v.
Okay, all right. And of course, you need to know what you're trying to fill in. But everything more or less is given to you. So 500 nanometers is the wavelength. B is 0.4 meters. Please change it all to the same units. Right, everything to the same unit. So this is in meters. This one is also in meters. The distance though, what's the distance? The distance will be from the sources to the instrument, right? So the distance here is 300 km. Right, it's a spy satellite. It's trying to read stuff on Earth, right? It's trying to look at stuff on Earth. Okay, so can you calculate out for me what this means? Right, how much is the smallest separation, which is x now? Sorry, I actually got another lesson later, so I'm eating first. What do you get x as?
0.45.
Okay, what does this mean? It means that, okay, I'll give you an example. Let's say you got a car next to another car. Then you got a spy satellite. Right? Let's talk about the gap between the cars. So the smallest gap that the cars can be is 45 centimeters away. 45 centimeters away. That means the cars must be this distance away from each other. So the end of this car and the end of this car like this. Then the camera in space, right, the satellite camera in space will be able to distinguish one car from the other car. If these cars are very, very close, lesser than 45, let's say they're 30 cm away from each other like this. Okay, let's say they're 30 cm away from here to here, right? They are this close, 30 cm. The camera, right, will not be able to distinguish that there's a gap in between. The camera will think that there's just one long continuous object. Yeah, or maybe two cars stuck to each other, right? A limo. So it's one long rectangular thing. So the camera won't be able to resolve such pictures. The camera will just show you a blur image of like a fuzzy image of just one long vehicle. Okay? That's what resolution is, right? For a spy camera is all about. Yeah? Okay? Of course, if the cars are further away than this, let's say the cars are 60 cm away, the camera can obviously tell there's a gap in between. That means there are two cars lah. Yeah? Okay. So that's what it means. All right, let's do the next one also. Headlights. Let's try to um, get you to do this on your own. Okay. Yeah, anyway, the 9,000 meters is wrong one. Do you get the answer already? What's the answer? Yeah, 7380 meters. Right, distance is 7380 meters. Everyone got this? Denise? Got it, huh? Okay? Yeah. Okay. So, you all have the, I think you all at this point, you all know how to calculate most of these kind of resolution questions, right? The next thing that I think, just one thing that I want to point out to you guys is, some students, after a while, right, they get a bit perturbed by this kind of statements. Like, what's the maximum distance? Maximum distance that the two headlights can be differentiated from each other. Don't worry about this kind of words here, right? Maximum distance meaning that, what's the maximum distance that you must be away from the car in order to differentiate the two headlights, which you have just calculated to be what? 7380, right? 7380? 7380. I mean, what happens if you step back and then you go to 7400? Then it will look like one image, one spot of light. Okay, then you won't be able to distinguish that there are two headlights. But this is maximum distance if you consider how far you can go away from the car. I change the question and say that what's the minimum distance so that you can just distinguish the two headlights? No, the minimum distance when you're walking towards, right? Then it's like, they'll just try to change up the words. So don't worry about the words. Okay, don't worry about the words that they use. Just understand, yeah, they're looking for just resolve lah. 1.22 lambda over b equals to x over d. That's it. Okay. But what if they ask you questions like, can this be resolved or can it be resolved, right? You calculate it separately. You calculate the 1.22 lambda over b and you calculate the x over d, and then you compare the angles. If you know that the instrument angle is smaller than the angular separation, then can be resolved. Okay, Okay. One more thing. You know when you use this equation, right? What's the units of theta? Radians, not degrees, radians. Okay, radians, because these are all small angle approximations, so they're always in radians. Okay, right. Just do this also, and then you can take a quick break after this, and then we go into resolvance. Okay, just do this one here, and then we are done with resolution already. I think the drawing is the one I want to go through. So you're asked to draw this. Just make sure you draw the 2 points here. And you just curve it up like that. Okay? Right? So the most important 2 points are the central max and first minimum. Right? And you just curve it up like this. Try to draw something that looks a bit symmetrical, then that's it. You can already. No problem. Doesn't matter whether you draw on the left side or right side, it's the same. Ethan, you okay or not? Damn shag ah. What happened? PE? What did they make you do at PE? Shag. I have trouble trying to do 5. Walao, it make you do 50. Then what else? What else happens for PE these days? You go school now today?
Yeah, I did, but I went home first.
What time do you finish school?
I forgot. I think 3:20.
Oh, still need to cut hair. Oh, hair very long, no? No, cut hair, two of you.
Oh,
Oh, weather so hot. Do cut like that lah. Can you tell me what's the answer for this one? What's the size of the slit used? 3.7 negative 6 meters, is it? Okay. Did everyone else get that? What do you get, Ethan? Okay, hang on, huh? No, hang on. So the first question is, do you use 1.22? A single slit, so it's not supposed to use 1.22. What equation do you use? Right, single slit, right? Single slit is just theta equals to lambda over b, okay? Single slit. Now what's theta do you use? So the theta is the spread, right? From central max to first minimum, right? What's your theta that you use? 0.17 radians, then also you're also wrong. Because it's 0.17 milliradians. Do you see the M right there? Oh, wow, like one layer, another layer of trickery, right? So you just have to be very careful, okay? Right, don't worry, I know you're tired. Okay, don't worry, right? So I understand this. So like you just have to learn how to be very careful whenever you do the calculations in the exams. Okay? Yeah, okay. So what's your answer? 2.94 times 10 to the power minus 3 meters. Okay, good. What's the distance from the slit to the sources? That means what's D? Because they say for just resolved, right? So it's already just resolved already. So what do you get for D?
I think.
176.4 meters. Okay, can I mean, it's night time now. I guess in a way, resolution can be thought of as this. Let's say you're looking at a tree, right? And you're trying to distinguish the two little leaflets on a tree. Let's say we're talking about those trees with very small leaflets, right? Like, are you able to resolve the two leaflets? The answer is no, right? But that's not because your eye hasn't, it's not because your vision is poor or anything like that. It's because the resolution of your vision is not good enough, right? You need a bigger instrument. Okay? Denise? Calvin? Issues? Issue. Okay, so basically it's lambda over b equals to x over d. There's no 1.22. Because single slit, still single slit. Right? You get this? Right? So there's no 1.22 there. Can Alright, so just take note of that. So it's based on the instrument. So if the instrument is an aperture, then yes, you use the 1.22 lambda over b. But if it's a single slit, then you just use right the lambda over b, right? The resolution of a single slit. Okay lah. Can. You want to take a quick toilet break? Yeah, quick toilet break, go. Right, then I finish up today's lesson with Resolvance. Right, then next week I do Doppler and I try to do a bit faster. I may do the tandem lesson like closer, maybe in August soon. I mean soon Maybe I just do it for 1 or 2 weeks just so that I can double up the lessons. Can you let me know like approximately sort of like when like ah. Oh, okay, can, good. Then I'll do it after that lah. Great. Can? Wait, what?
I don't know that.
Can. Ian, do you have soccer on Mondays?
No.
Oh no, I don't have that. How was your physical on you went for physical test, right?
Then
Health checkup, right?
the doctor extended my MC for like safety, but then now I'm not allowed to train again because my teacher found out that I have MC.
What's wrong with you?
I tore a ligament in my quad because my senior like smashed into me.
Shit. Wait, ligament and quads
Like the front side. Somewhere.
How do they detect that you have a ligament tear there?
Huh?
How do they detect that you have a ligament tear? How do they know that you still have a ligament tear?
It's no longer torn, but like there's some weird like calcification thing around the ligament.
Shit.
It's going away slowly, so it's okay.
So it's been going away? Guarantee it's been going away.
Yeah.
Okay. That means you have to do ultrasound
I did ultrasound, then I did MRI.
No, as in like how about the therapy?
Oh, I just did physio.
Physio can get rid of calcification.
Oh no, calcification can't be helped. Like I just did like polio myself.
Okay.
Not so bad. But then I went to play like during my MC, but then my mom and I said my teacher my MC. I got into a bit of trouble.
With who?
My teacher, because I never said in my MC.
Okay lah, teacher will be okay lah. Yeah. Then you at least can go for some training, right? Some light exercise, right?
Because like the MC officially is until 25th. Then I cannot ready for the rest of it.
When's the next season? Next year lah.
Yeah.
Next year. So you're trying to hopefully get into the next season lah. Okay. Oh yeah, this person I was talking about earlier today was this guy was like I think Okay, come. You guys ready? Let's do resolvance. Okay. You see the word resolvance? You see the word resolvance? Please understand resolvance and resolution are again two different things. Resolution is for a single slit or single aperture. Right? That's resolution. Resolvance is for diffraction grating. There's no such thing as resolution of a diffraction grating. There is also no such thing as resolvance of a single slit. Right? The word resolution is for a single slit. The word resolvance is for diffraction grating. Can? Okay, good. Tell me again, diffraction grating, what are the two uses of it? Two uses of diffraction grating. Right? Find wavelength of unknown light and what? Separate colors, to separate colors, okay? All right. So let me help you out here. Understand that resolvance of diffraction gratings is the grating's ability to separate colors. So some gratings are good at separating colors, some are not so good at separating colors. Right? In general, if you have those gratings that have more lines per cm, right? More lines, that means that more gratings on, right? That means the gratings are much closer, right? If you have more lines per cm, then those gratings are better at separating colors. Okay? Okay? So this notes here, useless one, you draw your own. Right, you draw your own. Okay? You draw a diffraction grating first. This is how you draw it. From the top view, it will look like that. This diffraction grating, multiple slit, right? Multiple slit. You draw a screen, right? Diffraction grating and screen. And what's resolvance again? Good. Grating's ability to separate colors. So I'm gonna ask you this, okay? So you want to separate colors that are very close in wavelength. You wouldn't be concerned about, let's say for example, two colors like red and blue. I mean, what's the wavelength of red? 700. What's the wavelength of blue? Around 400, right? 450. Like violet is 400, right? So the general idea is that you wouldn't be trying to separate colors that are very far away from each other. Red and blue very far away from each other. 400, 700. The difference is 300. You're trying to separate colors that are very near each other. Okay? Right. So I'll give you an example. Okay, this is just arbitrary example. Okay, orange and yellow. Right. I give you orange light. I give you yellow light. Right, in the same beam of light. That is very close to each other. Right, and I shine it onto a diffraction grating. Okay. Okay. First question. What do you see right in the middle? Like here. What do you get right in the middle there? White light only when I use white light, right? Right. White light will give me constructive interference of all the colors. That's why it's white. What? But now I'm giving you two colors only, orangey yellow light.
You see orangey yellow.
Yep. Combined, right? They're both combined, right? So both the orange and yellow dot are combined in the middle like this, right? They're just like combined in the same spot. So at the center, right, are they resolved? Are the two colors resolved? No, they're not resolved. Okay, but then you have to look at the side. You look at the higher order. Let's say we look at the n equals to 1. Okay, let's say we look at the n equals to 1. Let's say the n equals to 1 is around here like this. Okay, all right. Question. For the n equals to 1, right? The orange and yellow, which one is further away from the center?
Orange.
Why orange?
Because it will have a longer wavelength.
It has a longer wavelength. So d sine theta equals to n lambda, right? Good. Right? Orange has a longer wavelength, so orange will be like further away from the center. So it will be like this. But maybe the first order, right? They're still very close to each other. Look at that. Right? I still make it very close to each other. Maybe I will think that this is still not very resolved yet. That means they're still not distinct enough yet. They're very close, but they're still not distinct enough yet. What do? I look at a even higher order. So the idea of resolvance is the higher order that you go, right, the further away the colors go from each other. So maybe at n equals to 2, right, maybe at n equals to 2, they are far apart enough for us to distinguish that, hey, these two dots are separate like that. Okay, you see the separation of the two colors gets a bit more now. Can? Okay, right. So I'm just drawing this for you. I'm just trying to show you, right, on the other side here, n equals to 1, right? The orange and the yellow very close to each other, and then the n equals to 2. The orange and the yellow are now further away from each other like that. Okay, something like this. So it's just the ability to distinguish two colors from each other, right? Distinguish two colors from each other. Can, right? The example I'm using here is red and yellow and orange, yellow and orange. All right, data booklet. Look at the data booklet. Give me the equation for resolvance. Since we are talking about resolvance, let's talk about the equation for resolvance. Come, read out to me the equation. Eh, I will always have data booklet. Yeah. Read out the equation, come. R equals to lambda over del lambda equals to m small m times big N. Okay? Can right. What does R stand for? Resolvance. Okay? Resolvance. Alright. I'll tell you now, the number, right, is useless one. Whether R is 1000, 2000, 3000, 5000, 200, 300, there is no benchmark to what R is. Okay? In general, right, as with most things, the bigger the better. Alright? If R is bigger, it means better resolvance. That's great, but you shouldn't think of R values like this. Alright, let me show you how to think of it. Okay? So you just ignore R for now. Let's talk about the wavelength. Let's talk about this lambda here. Down here I got two wavelengths. I got red color, I got orange color and I got yellow color. Right? But there's only one lambda there. So what should it be? Now some teachers will say that this lambda can be either one of them. I don't agree with that. You just take it as an average between the two wavelengths. Yeah, you take the average between the two wavelengths. So to understand this, read the last question. Okay? So before you write down anything, just read the last question first. Let's look at the last question there. Right, what's the last question? The last question says this. Two lines in the emission spectrum of sodium. Okay, hang on. Before you read any further, right, you might be thinking, what in the world is this? Have you done chem emission spectrum already?
No.
No? You haven't heard of the word emission spectrum in chem yet? No. You have? You have? How come you haven't? Wait, is it just recently only? From long time ago, right? Huh? Where? The most recent chapter. Okay. No, it's fine. The order might be different, right? Okay. So if you don't understand what this is, don't worry. Basically, it just means this. Sodium produces two colors. Right? Sodium produces two colors. Two lines in the emission spectrum of sodium, it means that sodium produces two colors. How does sodium produce colors? When you burn it. Okay, let's say you take a piece of sodium metal and you drop it on water. What do you observe? You should know this, right?
That's it, no?
You don't say that it becomes fire lah, right? No, this is not Avatar, right? Not the last airbender, right? So you become fire. No, right? What you have to describe it nicely, right? You say that the sodium metal floats on top of the water, then what does it do? It reacts violently, produces, okay, produces whatever, sodium hydroxide, right? Okay, but what's the color of the flame?
Orange.
Okay, yeah. Are you able to tell that this is orange? And red is what wavelength? 700, right? Okay. Red is 700, okay? So this is like, and green is 550. So this is somewhere in between orange and yellow. So the sodium produces a flame that's orangey yellow in color. So if you take a piece of sodium and you burn it, right, it will produce an orangey yellow flame. Hey, you understand this, huh? My point is this. My point is this. The color that they produce, right? How do you know whether or not it's monochromatic? What does monochromatic mean?
One color.
One color. How do you know there's one color or not?
Has one wavelength.
I mean, how do you know? Use diffraction grating. So the light that you pass through, right? You use a diffraction grating. Your job is really to just split the colors to see whether or not you can see two distinct dots. To know that whether or not the light that it produces is a single wavelength or more than one wavelength. Okay, so diffraction grating is used to split colors. But whether or not the diffraction grating is good enough to split these colors, right, depends on this equation here. You understand this? So when you use this equation, lambda would be the average wavelength between the two colors that you're trying to find, right? 604.0, 604.5, right? Just average. So the average is 604.25. Okay? Some teachers will say it doesn't matter which one you use, and I agree with them. 604.0 or 604.5, you can use whichever one is fine. IB also thinks it's fine. But it's just that sometimes, right, you really don't know whether or not you should use 604.0 or 604.5, right? You just use average. Okay, so you can use average for this one here. What does the lambda mean? The difference. The difference between the two wavelengths. I mean, if let's say I give you red and violet, okay, what's the difference between red and violet? Like in terms of wavelengths? 300 nanometers, right? Right, 300 nanometers. It's such a big value. Don't have to worry about that, right? I'm very sure you know how to distinguish between red and violet. Okay? If you put red and violet into this thing here, right? Into this diffraction grating here, the red will like be on this side and then the violet will like be on this side. It'll be very far away from each other already. Okay? Alright, so we are concerned with those wavelengths that are very near each other. So what is the spread, right? What's the difference of the wavelengths here? 0.5 nanometers. It's very, very near to each other. That means these two colors, right, in reality, they look almost the same, right? But they have different wavelengths, and we need our diffraction grating to kind of like distinguish between the two colors. Okay? All right. And the general rule is this: the smaller the difference, the bigger the resolvance required. That means if you have a very small difference in wavelength, right? That means they are very, very close to each other. You need a very big R number. Write that down. That's the context. That's the context of resolvance. If delta lambda is very small, then we will need a very big R to be able to resolve it. Okay? So when you take the lambda and you divide it by the del lambda, you get an R value. You need to meet this R value. You need to be able to meet this R value. How do you meet the R value? You take the M multiplied by the N. Okay, right? This R value, right? So lambda divided by del lambda. If del lambda is very small, then you need a very big R value, right? And you need to meet this R value to resolve it. If you don't meet this R value, you won't be able to resolve. So in order to meet the R value, you need to take this small m times the big N. What is small m?
Order of the diffraction.
So you read that on my notes, right? Small m is order of diffraction, right? Okay, okay, this is the part where I really don't like IB with regards to this topic. They mess around with a lot of the letters. You know, we've been using n equals to 0, n equals to 1, n equals to 2, right, all the time, right? So now they're saying that, okay, please use small m. That means it's the same thing. It's basically just me rewriting this to m. Like that. That's confusing, right? Okay, never mind. I confuse you more later. For now, right? For now, you just okay. This m in this equation and this n in this diffraction grating equation is same thing, same exact same thing. Okay, so far? Can right? Okay. What should m be then in order to get r as big as possible? Right. So the higher the order, the better, right? The higher the order, the better. That means at higher order. I mean, look at the picture I drew for you. Does it not show you that at higher orders the two dots gets further away from each other? That means the bigger, like it's more distinct, right? At bigger at higher orders, right? You can distinguish the two colors, right? At higher orders. Yeah, okay. So the idea is, if you observe higher orders, it's more likely to be resolved. The two colors will be resolved from each other. Okay? But I must go through a couple of things. There's a limitation. Can I just say, oh, you know what? How about M? I go 10 order 10, like, you know, M equals to 10. Cannot. How about 20? How about 30? How about 40?
No.
Why not? You said no, why not? Okay. Yeah, oh yeah. The angle cannot be more than 90, right? There's a maximum order you can reach, right? I mean, the one that I show you, the violet laser on the diffraction grating, right? Like, what's the maximum order you get? You get 2, right? You can't even see the third order, right? I can't even see the third order from my diffraction grating. So there's a limit to the maximum order that you can. But what's the question here saying? The question here is saying, right, if you want to resolve it in the third order spectrum. So all the questions are like that. For resolvers, right, IB questions are all like that. They just ask you, you want to resolve it in the third order spectrum, you just accept the fact that the third order can be reached. That means N can be 3. Can? Right? But don't go and can go and say, hey, 4 lah, how about that? Or 5 lah, how about that? They say for 3, then you just take it that can reach 3 lah, can already. Okay, huh? Okay. Then the next one is this N here. Oh, wait, so sorry, one more thing. So the higher the order, right? Another problem is the higher order, the intensity very weak already. Very hard to distinguish, very hard to see. Okay, that's another disadvantage for higher orders. All right. Okay, but what if N? Big N.
Number of slits per.
Oh, no. Read my notes there. What does big N stand for? Number of slits that's been
Covered by instant.
illuminated. Right? Number of slits that's been lit up.
How do you tell?
Yeah, how do you tell? So like in this picture, where is this big N? In this picture that I've drawn in this picture that I'm assuming that you also draw, where's this big N? This N is within this region here, right? Within this region here, which is covered by the light beam. So the light beam must have a certain like width. It's not infinitely narrow. It's like a beam of light, right? And if it's a beam of light like this, then it covers this amount of slits, cover this amount of lines, right? And that's the N. Now, how do you make N as big as possible?
Don't use a laser.
You can, yeah, don't you can use a bigger light beam. That's true, you know. That you can use that for better resolution, right? You actually can use a bigger light beam. Okay? The reason is this. If you can cover more slits, means you have more lines, means more sources, right? More sources means that the fringes are brighter. If the fringes are brighter, means they're more distinct. That means you can resolve it even better. All in all, right, I'm just going to tell you this, okay? Everything has been derived already, right? At the end of the day, you just need to know how to use this equation. Like the derivation for this equation is super complex, right? They talk about what, how the peaks of the things are, like how far they must be and all that. It's been simplified into this equation. But you don't have to derive this at all. You just need to know how to use it. Okay, can right? So you can use a bigger beam of light, or yeah, like you just change the grating lah. Not that you can go and right, not that you go and cut the thing, right? You just go and buy another grating lah. Go and buy a better one. Go and buy with like 1,000 lines per mm type, all right, or maybe 2,000 lines per mm type, right? So as long as you have more lines per cm, you can get more. You can get more like lines illuminated, right? Okay. So by doing that, by observing a higher order, or by increasing the number of slits, right? By changing the grating, I can therefore meet the R that's required to resolve this wavelength and the spread. Okay? Okay, huh? All right. So, all right. So now we solve this question using this equation. Like the whole idea of what I was doing just now was to help you understand what's going on. Now we just use it, right? I mean, everyone can use this equation, but if you don't know what's going on, also you might make a mistake. So they want you to calculate the number of lines per cm needed for diffraction grating if you want it to resolve in the third order spectrum and the beam is only 2 cm wide. Okay, so first things first, let's just plug in a value that we know for this equation. Right, what's the values? Right, 604.25 divided by 0.5. Notice how I can just ignore the nanometers because they cancel off. Right, and then this is equals to, I want to observe the third order and I don't know what's the number of lines that I need to illuminate by. So we need to find n. Okay, can you find n for me, please? Okay, so what's n? Right, this is not complicated math, right? So what do you get n as? 400 and, can you get the decimals? 402.8 lines, right? Okay. Now I must get you to understand this, okay? Even if you get 402.2 or 402.1, right? Do not round down. Because this is the minimum number of lines that you need, right? To get this resolvance. Right? This is the resolvance required, right? So if you round down, means that you're not able to resolve the two colors if you go with 402. So this one here shows you that you have to round up anyway. So always remember to just round up. Just round up by the one, right? It's fine one, okay? So then the next one will be like lines per cm. So the whole idea here is you need 400 lines in this, within this width of the beam, right? You need 400 lines, okay? 403 lines, sorry, right? The beam is 2 cm wide. It is 2 cm wide. So they're asking you, so how many lines does this diffraction grating need per cm? So you just take 403 divided by 2 cm lah. Or you take 402.8, then divide by 2 cm, right? What do you get?
Oh shit.
Why? What do you do? 201.4, right? So even though you got 201.4, when you round, you must round it up to 202. Bro, I told you already, right? This thing, the nanometers, you don't have to worry. The top nanometer and the bottom nanometer cancels off. This thing, nanometer, the difference also in nanometers. So 604.25 divided by 0.5. Okay. Then resolvance. Can? Right? And then use your revision village. Use the revision village. Wow, power lah, this one, this resource. Someone kind enough. These all appeared in the last couple of months only. Like last 1 or 2 months, right? You know, people started torrenting it, you know, and it's like, wow, okay. Yeah. You can get it also. I like the style of the questions there because they are very reminiscent of the actual IB MCQs. Yeah. Actual IB MCQ, they like to play a ratio. Let me show you. So where did we do? Wave phenomena, resolution release criterion. Let's look for this is medium, medium difficulty. Okay, let's try this. Come. Two light sources emit frequency of light. F. Light passes through circular slit. See, the problem with some of these questions, right? Some people think, hey, is this two source interference? It's not. It's not two source. It looks like, right, but it's not two source interference. This is actually resolution. So a lot of times, right, your job is to distinguish which chapter is it from. That's why I don't like it when they start jumping around like that. It's very confusing, one. Like, you just go in sequence, teach everything, right? Never mind. You learn everything modular, okay? You learn everything modular. Don't worry. I'm just very surprised that you guys have to go and do topic 3. Jeez. So I'll be teaching topic 3 lah for the promos. Yeah, you'll be tested anyway. But meanwhile, for the test, you just go and you hit this practice and let me know if you need help. Yeah. Images of the light sources are not resolved. So which of the following changes allows the images to be resolved? Make sense, right? Huh? Answer. Like you want better resolution, right? What would you do to achieve better resolution? Yeah. So which options? What? Hey, I think you're very tired. Come, Jia, your turn. Okay, 2 is wrong. Yeah. Alamak, your Sec 3, Sec 4 EM spectrum, jialat sia. Increased frequency of light means wavelength shorter. Right or not? Wavelength shorter. That means like UV, right? UV. So correct or not? First statement is correct. Right? Increasing frequency will decrease the wavelength. Right? Having a smaller lambda is good because the instrumental spread will be smaller, right? The fringe will be narrower, right? Okay? So okay, good. This one, angular separation, make it further apart, yeah lah. Right? Make it further apart, definitely better lah. Right? I mean, if you can, of course, you go and make it further apart lah, right? If you can, you make it further apart, so therefore it'll be better resolved lah. Cannot. Right? This resolution. This single slit. Then down here, there's only one slit. Resolvance is for diffraction grating. Right or not? Okay? Alright, so I mean I can show you the resolvance one. Where's the resolvance one? Yeah, let's try this one. Let's say it's hard. Okay, beam of light containing a narrow range of wavelengths illuminates the diffraction grating. Okay? Alright. So there's a narrow range of wavelengths, which is like the del lambda that I was referring to, right? Okay, the smallest differences between the wavelengths that can be resolved in the third order diffraction is 6 nanometers. Which of the following wavelength differences can be resolved when the first order diffraction is observed and if the number of illuminated slits is double? Wow, that's why this one's hard. Because this one is very reminiscent of the IB type of questions. Yeah, you read the question first, then I'll guide you through. Right, I'll guide you in a while. Right, don't worry. Right, I'm gonna help you here. Okay, can? When you encounter this kind of question, so this is the IB standard question, like not this question specifically. This question is hard, okay? But the IB standard is this, they like to play around with ratios. So you write out 2 equations first. There are 2 scenarios, right? There's a first scenario and a second scenario, right? You focus on the first scenario, right? You know there's resolvers, right? Give me the equation. Lambda over del lambda equals to mn, right? Okay, let's just try to fill in some numbers. Okay, what's the del lambda? So the first one is 6 nanometers, right? 6 nanometers. I just put 6 nanometers here. Then the order is what? Third order, right? Okay. Then the number of slits is just the number of slits n. But we don't know how much is it. Doesn't matter. We just leave it here first. Right? Learn how to deal with unknowns. Okay? Learn how to deal with a lot of unknowns. Then the next one. Okay, now we write the next equation. So same wavelength, they didn't say the wavelength change, but I need to know what's the new spread, right? Because that's what they want me to find, right? What's the new range of wavelengths, right? New spread of wavelengths. So the lambda 2, right? equals to, somewhat, the next one is what? First order, right? They want you the first order, so you need to put 1. Okay? And the number of illuminated slits is 2 times n now. 2n, correct or not? You read first, and see whether or not you can fit it into this. Can, right? Okay. So scenario 1, scenario 2, objective, what are you trying to find here? What's the thing that you want to, what's the unknown here that you're trying to single out? You want to find out this one, right? Okay. Right, play around with this one, go and try to find the lambda 2. Yeah, just find the answer first. That's not the final answer yet, but you just try to find the answer first. Right, the lambda 2 equals to what? So yeah, okay, so the next thing, the next skill that you need to learn is this. What's the common term between the two of them? What you throw? What do you throw? Okay, what's the common term between them? It's either the n is common or the lambda is common, right? So whichever way you want to sub in, you sub in lah. Doesn't matter, right? You sub in. You should be able to find an answer. Yeah. Oh, 9. 9? Is he right? 9? His sing song not bad. Abacus. Grandon, yeah, Grandon. Grandon's abacus skills can only help him until so far one lah. Walao, these things are getting more complex already. Right? It helps you with the math and all that, but then like to understand what the heck they want here. Right? Different ball game already. IB standard, 1 scenario, 2 scenario, find the common term, right? Manipulate it until you can find whatever you want to find. The lambda 2, what's it? 9 right? 9 nanometers, right? So his mental calculation is correct. 9 nanometers. Okay? What they're saying is, in the new scenario, right, when I look at the first order and I double the number of illuminated slits, right, the range that I can resolve is 9 nanometers. So the idea is it cannot be more than this. If the range, right, if the range is bigger than this, right? Sorry, it cannot be less than this. Yeah, the spread must be 9. The spread cannot be less than 9. Remember what I said about the lambda? The smaller the lambda, what happens? What did I say about the lambda just now? The smaller the lambda, the bigger the R I need, right? Okay or not? So in the second scenario, the lambda that I can resolve, right, is the range of 9 nanometers. Anything smaller than this, I don't have enough. I don't have enough, right? My resolvance is not high enough to resolve anything smaller than this spread. Okay, so 9 and 12 can be resolved. If the spread is if the spread is nice, just nice can resolve. If the spread is 12, even better, confirm can. You understand what I'm saying? Okay. All right, check the answer. Right, answer is D. Okay. So yeah, wavelength difference. See what the answer says. Wavelength differences that are greater to or equal to 9 can be resolved. So it's 12 and 9 can be resolved. Can Okay, good. Right. So please go ahead and make use of this. Yeah, make use of this thing here. All right. So I'm gonna just do a bit of revamping of my shared drive because this came to me over the weekend only. So I would suggest that you use this, right? But this one is a bit harder lah, and it's quite short also. But I think it's good enough, right, for you to understand the things. And for promos, we will have to do the past year papers. Okay, we have to start doing past year papers soon, and I'll probably give you a full paper from the past years also. Okay.